Enzyme kinetics is a high-yield topic. We give it a 4 out of 5. You really need to understand this before you go into your boards. Enzyme kinetics is the study of enzyme-catalyzed reactions. It's important to understand because it helps explain how enzymes work and also predict enzyme behavior in the body. The Michaelis-Menten model of enzyme kinetics is also very high-yield. It is one of the best-known models of enzyme kinetics that we have, and it is the basis for most of our understanding and the way that we teach single-substrate enzyme kinetics. Let me introduce what we're talking about. There is a picture on the right that shows 3 different reactions, each one of them with varying concentrations of substrate, but a constant concentration of enzyme. What we want to know is how does this enzyme perform under different situations, such as with a change in substrate. This is what enzyme kinetics is all about. How will the reaction on the far left differ from the reaction on the far right? So this is a graph that is going to demonstrate the relationship between substrate concentration and reaction velocity. And we're going to do it using the Michaelis-Menten model. From the curve that we're going to graph, we will be able to deduce things about properties that the enzyme and the reaction has, such as what is the affinity of the enzyme for the substrate? What is the potency of this enzyme? How would the reaction change with the addition of a competitive or a non-competitive inhibitor? So the first point to understand is that enzyme-catalyzed reactions are saturable. What that means is that the enzymes can only do so much work. There can be such a large increase in substrate concentration that the enzymes can't keep up. That means that we do not get a linear response to the reaction velocity from an increase in substrate concentration. So let me demonstrate what's not happening. Let me demonstrate what a linear reaction would look like. These red dots represent individual reactions. Remember, we're not dealing with one reaction and watching it chronologically with a change in substrate concentration. We're actually sampling multiple reactions in multiple test tubes with a sequential increase in substrate concentration. And we're only really measuring the very initial phase or the very first part of that reaction. And then we plot those numbers and draw a curve. So here is 4 separate reactions. Each one of these reactions would have had a different substrate concentration in the test tube. You can see that in this false example, there would be a linear relationship between increasing substrate concentration and how fast the reaction occurs, or the reaction velocity. This is not the case. This is false. What we actually see in real life is a curve that tapers as the substrate concentration increases. And the slope of that curve eventually levels out so that it doesn't matter how much more substrate you add, the reaction will not go any faster than that point. And that is called the Vmax, or the maximum velocity. Vmax is important because it helps us understand the efficacy of the enzyme or the drug if we're using this model for pharmacokinetics. But we also need to know the Vmax so that we can calculate half Vmax. Half Vmax is as simple as it sounds. It is located halfway between the value or the rate or the reaction velocity that is Vmax and 0. So halfway between those two, we have half Vmax. Sounds easy, right? If we were to put a point on the curve on our graph at half Vmax and then draw an x-intercept or a line straight down from that point, we would find another important value. This would be the Michaelis constant, or Km. So now that we've defined these terms, let's change graphs and play with these values, move them up and down and see what happens. So now that we've defined and talked about some concepts, let's relabel our graph with those things that we've talked about. What is Vmax and where is it on this new graph? It is a line that intercepts the y-axis. It is a reaction velocity or a rate, and it is placed such that our curve or our graph never quite reaches it. It approaches it but never quite reaches it. What about half Vmax? Yeah, so half Vmax is exactly halfway between that rate, which we call Vmax, and 0. What do we use half Vmax for? Well, we use it to find the Michaelis constant, or Km, and we do that by placing a point on the graph or on the curve and then running straight down to the x-intercept. The Km represents the affinity of the enzyme for the substrate, or the potency of a drug. An enzyme with a very high affinity for its substrate will have a very small Km, so they're inversely proportional. The larger the Km, the lower the affinity, or the lower the potency. So basically we're saying the closer Km is to 0, the faster that enzyme takes off. So this is interesting. Look what happens when we move the Km back and forth. And maybe this will make more sense if you can see it move. As the Km moves away from the y-axis, again, the potency is decreasing. The affinity is decreasing. Can you see that? Can you see how the steepness of the curve of our graph decreases? How the reaction just isn't taking off quite as fast? However, Vmax doesn't change. So you can still approach Vmax if you add enough substrate, but the speed with which it takes off, with which the reaction explodes out of the box, so to say, is slower. It still reaches top speed, it still reaches Vmax, it just takes off slower. So now we're going to start talking about inhibiting the system with a competitive inhibitor. Take just a second to think about how competitive inhibition works. Competitive inhibitors directly interfere with the substrate for binding sites on the enzyme. So the enzyme has to work a little bit harder to find the correct substrate. Well, this is going to increase the Km and decrease the affinity, as we've already seen. However, think about it. If you add enough substrate, if you just keep pouring it into the test tubes, eventually you will still approach Vmax just because you'll drown out all the inhibitor. Vmax does not change with competitive inhibition. However, the Km does, right? Because at very low substrate concentrations, the inhibitor is really going to mess with the enzymes. It's going to confuse them. Does that make sense? It's pretty cool, huh? Okay, moving on. Efficacy. I mentioned this before. What is it? Efficacy is or describes the relationship between a ligand and a receptor, or an enzyme and a substrate, and is also related to the maximum response. So what is the relationship with the graph or the curve that we have here and efficacy? Efficacy is demonstrated by the Vmax in this graph. So as the Vmax goes up, the efficacy also goes up. As Vmax comes down, efficacy or efficiency or maximum response also comes down. Another thing to make mention of, another thing to note, is that Vmax is proportional to enzyme concentration. That's what I mean there by enzyme in brackets, enzyme concentration. As the enzyme concentration increased in our little experiments, in our test tubes, the Vmax would also increase. There would be more enzyme to do the work. It would almost be like sharing the load amongst more workers. However, the Michaelis constant would not change. So again, let's talk about inhibition. Non-competitive inhibitors decrease the Vmax and decrease the efficacy. However, a non-competitive inhibitor does not change the Km, or the Michaelis constant. And it really does make sense if you just think about how non-competitive inhibitors work. They just cause a general slowing down of the enzymes without directly interfering with the enzyme and its substrate binding to the active site. So the graph looks something like what you see on the right. One more thing to think about in the inhibitor category. What would a non-reversible inhibitor look like on our graph? It would look a lot like the non-competitive inhibitor. Vmax and efficacy would go down with no change in the Km. How far down it goes really just depends on how much of the inhibitor is given and or how long the enzymes are exposed, and also if there is some source to replenish the enzymes. So what would it look like if we replenished the enzymes? It would go back up, Km would stay the same, Vmax would go up, and efficacy would go up. Lineweaver-Burke plots are another fun thing we can do with Michaelis-Menten kinetics, because I know that you're having fun right now. Basically, we take the same plot that we're used to, the same axes and the same concepts, but we apply them to a graph that looks different. So on the right, you'll see a picture of what you're used to. On the x-axis is the substrate concentration. On the y-axis is the reaction velocity. The Lineweaver-Burke plot is kind of similar, okay? We're still talking about substrate concentration on the x-axis and velocity on the y-axis, but the values are inverted, okay? So instead of the x-axis being substrate concentration, it's now 1 over substrate concentration. What does that do for the way we interpret this graph? Well, as the substrate concentration gets bigger, the fraction gets smaller. So we actually approach 0 as the substrate concentration gets larger or the velocity gets larger. Okay, so keep that in mind. So let's use the Lineweaver-Burke plot and go over some examples so that we understand it. The current graph that you see with this black line represents our starting point. But I'm going to add 2 new lines to this Lineweaver-Burke plot. And they are actually going to represent the previous 2 graphs that we did, the 2 curved lines. So here's the first one, and here is the second one. So first, let's talk about what we're looking at. Where on this Lineweaver-Burke plot is the Vmax? Well, think about what Vmax is. Vmax is a point on the velocity axis, and that would be the y-axis. It represents a reaction rate or a reaction velocity that cannot be exceeded no matter how much substrate we pour into the system. So as the substrate approaches infinity, the Vmax cannot get any larger. So where on this graph does the substrate approach infinity? That happens at the x value of 0. So the red dot depicts Vmax. What about the Michaelis constant? Well, the Km, or the Michaelis constant, is a substrate concentration that represents the affinity of the enzyme for its substrate. That is represented on the y-axis at the green dot. So the slope of this line is actually Km over Vmax. Let's shift some of these things around and see what happens. So the first thing that we're going to manipulate is going to be the affinity, or the potency. Do you remember how that looked on the previous type of graph? So look at our first example, the red example. The affinity, or the potency, was directly related with the Km. And as the Km moved farther away from 0, or as the Km became larger, the affinity, or the potency, of that enzyme or that drug decreased. How would that be depicted on the Lineweaver-Burke plot? Remember, the Vmax did not change, but the Km got larger. See how that works? The Km approaches 0 because we're dealing with inversed numbers. This is what the addition of a competitive inhibitor would look like. Now how about the efficacy? What if we play around with the efficacy of the same system? And again, this is the same thing that we did to the previous graph. What did that look like? Well, we decreased the Vmax without changing the Km. So how will a decreasing Vmax with a constant Km, how will that look on the Lineweaver-Burke plot? There you have it. Does that make sense? So this is what a competitive inhibitor would look like if we were to add it to our system on the Lineweaver-Burke plot. Pretty cool, huh? Great way to spend a Friday night.